Hello, we are the battery cycler senior design team. We're here to present our project, the battery cycler. So what a battery cycler is a testing device that many industries use in order to test the efficiency for batteries. So what is going to happen, the cycler consists of a charger, load, and Arduino to control. And it's going to constantly charge and discharge the batteries called cycles. Through this constant charge and discharge cycle, the battery will start slowly losing its capacity and start breaking down chemically. And through this loss of capacity, we can measure for the expected life expectancy of the battery. So what we're measuring specifically for the battery is the battery capacity. Capacity is defined as the amount of charge that the battery can store and is measured in amp hours or amp times time. We'll explain more how we're going to measure it.
So as we mentioned, one of the core components of the battery cycler is the charger. For the charger, we're using a constant current, constant voltage charging method, which you can see in this figure right here. The first step is we have a constant current going straight to the battery. This procedure typically goes up until the battery reaches the upper target voltage, which is found in its data sheet. You don't want to go over this one as you will risk overcharging and causing harm to the battery, which could be dangerous for the person itself. The second phase is the constant voltage charging, where in this case, the voltage of the battery stays constant, but the current slowly just drops off until by the end of this, you'll have a 100% charged battery. And this is a method that we'll be using in our circuits. The project requirements for this battery cycler are that the battery voltages must be within 2 volts to 4.1 volts. The charging and discharge current is from 5 amps, is up to 5 amps with 0.1 amp accuracy. And our goal is to have an output display, which will show at the end the battery capacity and also show the voltage and current entering the battery. All of this entire design should be powered from 120 volts AC, which is from the wall. And this will all be controlled by a microcontroller, which will be an Arduino. This block diagram gives a better overview of the entire system. As you can see, the first step is we're stepping down, or we're converting from AC to DC in order to power the 3 main components of our project, that being the charger, the discharger, and the microcontroller that's actually allowing us to control the said circuits. We'll go a little bit into the different control components that we're using to actually set these values, but the final goal is to have these chargers and dischargers interact with the battery in order to create a successful cycling system. The DC to DC charger that we're using is, as we mentioned, is using constant current, constant voltage protocol, but it is using an LTM8026 step-down regulator, which is a buck converter. Is essentially just meaning you're taking a higher input voltage and dropping it down to a lower output voltage, but we're with the final goal of getting this type of characteristic with the constant current, constant voltage. And this is all done through an Arduino for control.
So there are many types of programmable loads, such as constant power, constant voltage, and constant resistance, but our main focus for the load is to build a constant current load. Because this, in order to measure for capacity, we want a stable and constant current. And if once we have achieve a constant current, we can just simply measure for time and therefore measure for capacity, since capacity is current times time. In order to achieve this constant current load, we have an op-amp as a differential amplifier in configuration with MOSFETs in parallel to distribute the current. This load circuit is going to be applied at the drain voltage. The battery will be applied so that whatever the battery drain voltage changes, the constant current remains the same.
Here below in figure 3, you can see that we have another diagram. This is kind of like the block diagram, but represented with real world components. So that way you can get a better visual of what we're using and what our display would look like, as well as how each component integrates with both the charging and discharge circuits.
So currently we have our testings, our initial designs were through LT-SPICE. From LT-SPICE, we were able to go to breadboard behavior, and from breadboard behavior, we got our initial results that we will show later on. From the constant current load and the constant charger. Through these LT-SPICE simulations, through we were able to transfer to easy EDA and produce actual PCBs. So far, the PCBs have not been able to produce any accurate results, and we are still in the testing phase for that. Sometime later, we'll be able to try and achieve actual results. But so far, our breadboard results have produced a constant current behavior that we wanted to achieve, so we have that to base off on.
And now we'll go into a live demonstration of what we have so far.
This is like our constant current breadboard testing for the constant current load. Our goal is to apply a voltage at the drain of the MOSFETs and measure for a constant current behavior, or so that whenever the drain voltage changes, the constant current remains the same. So I'm gonna turn it on. we have applied a voltage of 4.1 volts at the MOSFET's drain. We're going to start decreasing the voltage, or theoretically discharging the battery. And as you can see, the battery voltage, the constant current remains the same. So we have, from this PCB, we are trying to duplicate its behavior on our actually printed PCB board. It does not produce any accurate results, but we have identified the issue and already ordered new PCB designs.
All right, and then this is our PCB for our constant current, constant voltage charger. As you can see here, we have the LTM soldered on the board. Currently, we're troubleshooting, and we're going to have to resolder everything because we're having some issues connecting the LTM with the digital potentiometer.
And here we have the display with some mock-up code on what our menu would theoretically look like. So you can cycle through the different battery chemistries we're trying to test, select that, and you can even select charging or discharging mode. And then once you select charging or discharging, you can set the voltage, and you can range it up however high you need to or however low. And then same with the current, you can go all the way up to 5 amps as we'll need in charging or discharging. And then right here, it's just going to display everything you chose, and that's going to be ususeful for later on. We're the battery cycler team, and thank you for watching.